Hi, today we will read about end-to-end sequence labeling via bidirectional LSTM and CNN-CRFs. This is written by Xueze Ma and Edward Hovey. I like to start by talking about the main contribution. So it gives a little bit about the background as to why this paper was written in 2016. It was accepted to ACL Main. And it's stating at the time, like state-of-the-art sequence labeling systems require large amounts of task-specific knowledge in the form of handcrafted features and data pre-processing. So what they have is saying like they created an architecture pipeline using Bi-LSTM, CNNs, and CRF. And their main contribution is their system is truly end-to-end, requiring no feature engineering or data pre-processing. And therefore it's applicable to a wide range of sequence labeling tasks. And the two data sets that they use is the WSJ Penn Tree Bank and the Connell 2003 corpus for NER. Yeah, so this is what he's doing. So I think like what I like to talk about in terms of like the main paper, like in paper reading in general, is like how the architecture works. So he uses like a CNN for extracting character level representations of words. So you have like the actual characters, right? And then they do a convolution, max pooling, and then this generates a vector. And the main architecture that they have is here actually. So the word embedding, character representation, this is generated by CNN. The word embedding would be done by the Stanford Glove architecture, and they have the forward LSTM, backward LSTM, and then these two would have generate like a vector each, and then they will be concatenated, and I'll give like an explanation in detail using my notes later, and then this would be fed into the CRF later, which will also go into detail later. So the pipeline goes this way. So now if we go to my notes, so just to give a little bit of background on what sequence labeling is, like an example here would be like a sentence: Tim Cook works at Apple. This would be an input. And the labels we have would be BPR, IPR, BORG, IORG, and O. O for other. And then like the goal for sequence labeling would be label each word for like labeling, right? So Tim would be BPER, Cook would be IPER. And like Tim Cook together, as we know, would be a person. And then B stands for beginning, I stands for inside. So now we know Tim Cook is actually part of a person. So that's like we're giving like context to these sentence. So now for the first part, we have the CNN architecture, the character level embeddings. So if we focus on the Tim, like the input characters would be T, I, and M, and it would, let's say like it would generate like 30-dimensional vectors, but like I will be simplifying it to 3 dimensions here. Like T would have like 3-dimensional vector, I would have 3-dimensional vector, M would have 3-dimensional vector. So now CNN uses actually filters to detect patterns. So like filter 1 would detect like capitalization patterns, like it will slide over T, I, and M and give a 0.85 score, right? Like right here. And then for filter 2 would detect like common endings. So T, I, and M, and then has a low score. So that's why this is a low score. And then they would have like 28 more filters. In total, you would have 30 dimensions, right? So for the first layer, the character level embeddings would be generated by this, right? So we would have a 30-dimensional vector, and then we would do this for all words. So Tim would have 30, this Cook would have 30, works also at Apple. And then now what we try to do is this step 2 would be like the pre-trained word embedding using the Stanford Glove architecture. This would generate a 100-dimensional vector, and then here like Tim word embedding would be like, let's say 100 dimensions, and then Tim character embedding from the CNN from above would generate 30 dimensions. So now we would concatenate them together. So now this would be 130 dimensions, right? So now for all words, we have 130, 130, 130, 130, etc. And now we have the Bi-LSTM later. So now, so if we look at the architecture, we have the word embedding generated by GloVe, the character representation generated by CNN, and now we're going into the forward LSTM, backward LSTM, and then the CRF layer. So to go back to my notes, so for Bi-LSTM, the LSTM processes sequence in both directions, right? The input is a 130 dimensional vector. So, forward LSTM, it'll be from left to right. In both directions, so Tim would generate like a 200 dimensional vector, Cook would generate 200 dimensions, etc. And backward LSTM, this would go from right to left. So Apple at Works, Cook, Tim, right? So now this would have information. So I think the idea is like it's tried to encode like context information. So like there's a relationship between and Tim Cook, and there's a relationship between like Cook and Tim. So the Bi-LSTM, the goal is to like basically have that information together, and then if you combine 200 plus 200, it would generate 400 dimensions. So at this point, you would have 200, like 400 at this end of this pipeline. So if we look at the LSTM architecture, right, that is generated. So if we have the input here and then the output. So here, this would be like 130 dimensions, I think, in our example. And then the output would be 400. Or I guess like maybe this would be 200. And then you run it again and then have another one for the back one. And then you concatenate these two together. And generally, like the formulas to update LSTM is time t or this. These are like matrices that you update via backpropagation. This is the bias vector. And yeah, so these denote the weight matrices of different gates for input xt, and these are the weight matrices for the hidden state. These denote the bias vectors. Yeah, and they're initially randomized initially and then updated later. So yeah, so here this would be 130, this would be also 130, right? And then this would output like 200, and this would output 200. So by the time the CRF layer happens, you would have 400 level vector. Yeah, so LSTMs can be dived into later. So now this is like where it gets a little bit, it can get potentially confusing. So CRF stands for conditional random field. Like the 400 dimensional vectors are projected to 5 scores. So how does it do that? I think it does it by this formula. W transpose times H plus a bias vector. So this is like initially randomized. This would be the input vector for the Bi-LSTM output vector. So this would be 400, right? And then plus V would be a bias vector of 5, 1. So to explain, the weight matrix would be 400 by 5 because we're going to transpose it. So the dimensions would be 5 by 400. And then the input vector would be 400 by 1. And then in linear algebra, if these two are the same, they cancel out and they would generate a 5 by 1 vector. And then now we have a 5 by 1 vector for the bias. So this would also be a 5 by 1 vector. So that's why that's what this means when you're projecting the 500 dimension vector to five scores. So now for Tim, we would have 5 scores for this. And then I think they're initially randomized initially, but they will be back propagated based on like the data at hand, and they will be like properly trained. So we have five of them, five values for each word. So Cook would have 5, Works would have 5, and the labels would be based on this. I think for this paper there are like 17 labels, but I have to double check. But like the high level this is what it's saying. So what does this mean? So this is like the emission scores. So the CRF, how it works is like you sum up the emission scores and then the transition scores. Emission scores means like you're going, what's the probability or what's like the correlation between Tim and BPR? It's pretty high, like 4.2, right? Because like we know Tim Cook is a person, and then like it's usually like the first name of a person, so that's why it has a high value. And then for the transition score, this is also like information, but it's like the BPR, IPR, BORG, etc. And start. All of this information is initialized randomly, but it's conveying information like what are the chances, like it goes from BPER and then to BPER, for example. It would be -5 because it's unlikely, but for IPER it's 5.0 because that is quite likely. So, and you get the idea, right? So here, like BPR, IPR is 5.0, BPR, BORG is -10 because it's virtually impossible, I think, for BPR to be followed by BORG. This makes no sense at all. For example, this is wrong and this is wrong, so that's why it penalizes the model. Start to BPR would be +3, so it's pretty good. Start to IPR is 0 because you need a B value to start the thing. IORG is also 0. Other is like it can happen. So I think what happens with the CRF, it does like dynamic programming. So dynamic programming is like you have all possible paths like forming a tree, and then you trickle down the tree, and then once you hit a leaf node, you have some sort of score, and you tell from the roots perspective, you tally up the score. Let's say like this is A, B, C, D, and then let's say A has the highest value. It chooses A as the highest value because that has the highest score, and then it scraps the rest. And then they use memoization, so you don't like do repeats and stuff. But like for the sequence, for it to happen, this is like one possible sequence. Like Tim Cook works at Apple, like BPR, IPR, O, BORG. So these are the possible tags, sequences that are labeled, that are associated with this word, and like it calculates like the emission score and the transition scores at each step. So then you would start, and because this is labeled BPR, you would have start BPR, so 3, right? So this is correct. Emission, we would go here, and then for Tim to BPR, that would be 4.2. That's why the score is 4.2. And then the next step, right, would be BPR to IPR, right? So that would be the transition score. So what's the score from BPR to IPR? That's 5.0. And then for emission scores is Cook to IPER. It would be 3.8. And then IPER to O, that would be IPER to O, that would be 2.0. Emission works O. So what's like the cost of emissions? It would be works at O would be 4.5, right? And then you get the idea, and then if we do the rest, you get a tallying score of 34.3. And then I have a second example, and the only difference is like this one. Cook's, it has a label BORG, and then like I think I said this before, but like if you have BPR and then another B tag, that makes no sense. So the model, like a properly trained model, would punish this. So here this would be -10, a big penalty. Yeah, so now for this, for let's say let's call this path B. This would have 16.1, and then it will be scrapped. We know like this path is like not really efficient, not doesn't have the highest utility. So we scrap this, and then we say path A or option 1 is the highest score, and then we do the rest for C and D, and then it traverses all possible sequence tags, all possible sequences, and spits out the highest sequence. So CRF will pick this one with 34.3. So the final output would be this. So Tim Cook works at Apple, BPR, IPR, OO, B or person name organization. So the high level, I think this paper is called Bi-LSTM-CNN-CRF, but I think CNN Bi-LSTM-CRF is a better name, because CNN does the character level representation, and when the word and the glove is the word level representation. Bi-LSTM is like the middle, and then CRF actually outputs like a tag. So here, what this guy does, I ask Claude to generate like the backpropagation idea. So if we do that again, how this works would be character level embedding, and then we have the CNN for the character level embedding. Word embedding would be here, and then these two will be concatenated to generate a 130 dimensional input vector. This will be fed into the forward LSTM, backward LSTM, and then the LSTM weights, and all of these would be trained, and then by LSTM output, this would affect the 400 by 5 matrix that we projected down to the 5 emission scores and the transition parameters, and then the CRF loss will be calculated using negative log likelihood. And then all these values, if you have like you have the predicted and then the actual goal, and then like if it's not, then it would basically trigger back propagation and then like climb upward using PyTorch, right? And then all of these would be updated. So that's like the main contribution. I think like the main contribution of this paper, like it says, it's like a very clean end-to-end architecture. So it's really interesting actually. Like you don't have to necessarily invent new architecture. You can organize what is already done and still get a lot of citations. I think this got around like 3,000 citations as of this video, and like for the author, just to continue my thought, the LSTM, CNN, CRF were not invented by this author, but he just organized it. Yeah, I think that's pretty much it. So here, this is a POS tagging. For English POS tagging, we use the Wall Street Journal PSJ portion of the Penn Tree Bank. They do a standard split like training data, dev data, stat data, NER. This would be on the Connell 2003. 4 different types of name entities: person, location, organization, and miscellaneous. They use the BioES one, beginning, inside, outside, and then other, and then singular, I think. Tagging scheme instead of the BioE2. And I think, yeah, I'd have to actually look at this data and see what's going on, but this is what it is. And then, yeah, it has the usual spiel of like how it does some like ablation tests, like the original one, the BIS, this is a baseline, the BLSTM, this is the second one, and then it slowly adds up like architecture and says like it beats like state of the art, not by too much, but I think like maybe like it's popular because it's so clean at the time. But this is a significant bump. It's 6%, which is like respectable. This one's also +4. In the model, it's the usual spiel, like how they beat state of the art at the time, what they reported. And then here, IV would be in vocabulary, OOTV. This, he explains this as well. Yeah, out of vocabulary words, like the vocabulary is like split into 4 subsets called in vocabulary words, out of training vocabulary words, out of embedding vocabulary, out of both vocabulary. So yeah, that's pretty interesting. And it's saying like it beat statistics of the partition of each corpus for POS tagging and the number of entities. So I think this is like explaining like how the actual partition size is. Yeah, feature engineering or data preprocessing reached state-of-the-art performance on 2 linguistic sequence labeling tasks comparing with previously state-of-the-art systems. Can jointly train a neural network model with both POS and NER tags to apply a model. This is like future work that he talks about. And I think that's pretty much it as to what I had to say. Yeah, okay, thank you.